Hello, here we are in zeros polynomial function, section 2.5, okay? So we're getting a little deeper into the polynomials now, and so we're trying here to find the actual zeros, because when we're graphing them, we might want to find where the x-intercepts are at. If you find the zeros, you found the x-intercepts. Okay, so let's begin with our objectives. First of all, we're going to use the rational zero theorem to find the possible rational zeros. Okay, and then the next thing we're going to do is find the zeros of a polynomial function. You're like, well, that's just a duplicate of the first objective. No, the first objective is just to find the rational zeros. But remember, zeros can be irrational or complex. Okay, so the first objective is just to find the rational zeros, if it has any. And then the second one is to find the remaining ones, if you will. Okay, so third objective is to solve polynomial equations. Alrighty, so the fourth one is use the linear factorization theorem to find the polynomials with given zeros. Okay, so that's basically the factored form of a polynomial equation. Okay, so we'll talk about that when we get there. And then we're going to use the Descartes rule of signs. Okay. Now, the Descartes rule of signs, I will tell you right now, it will not find the zeros for you, but it will find you the possibilities of the zeros, okay? It's kind of limited in what it can do, but it will find some of them, okay? And it's called the Descartes rule of signs. All right, so let's begin with our first objective, the rational zero theorem. So you've seen this before. If f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way out to a sub 0. Remember, that's just a generic form of a polynomial function that has degree n. Okay? Now, let's assume it has integer coefficients and p and q, okay, where p over q is reduced in lowest terms is a rational zero of f, then p is a factor of the constant term, a sub 0, and q is a factor of the leading coefficient. So in other words, p is all the possible factors of the constant term, the one without the variable, and then the q is all of the factors of the leading coefficient, a sub n. Okay? So example, let's use the rational zero theorem. List all the possible zeros, rational zeros, of f of x equals 4x to the, I believe that's fifth, plus 12x to the fourth minus x minus 3. Now understand, we're not actually finding the zeros in this function. Okay, we're not going to do that. But what we're going to do is, if this has a rational zero, if it does, then it belongs to this subset. And you're like, well, that doesn't do us much good. Well, it does a little bit, okay? Because a lot of polynomials will have a rational zero. And so if we can find one or two sometimes, that's enough information to find the remaining ones. So in here, we're not even going to find if they are or not. We're just going to see what are the possible ones. So this one's going to be very limited to what we're going to be actually doing in this example. So the constant term is -3 and the leading coefficient is 4. So the factors of the constant term is of the plus or minus of -3 is plus or minus 1 and plus or minus 3. Because 1 times -3 is -3 and -1 times a positive 3 is -3. So those are all the possible factors of the constant term, -3. Now the factors of the leading coefficient, 4, is plus or minus 1, plus or minus 2, plus or minus 4. And you can determine that by looking at all the plus and minuses of those numbers. For example, if you have positive 1 times a positive 4, -1 times a -4, those are both 4. Positive 2 times positive 2 is positive 4, and -2 times -2 is positive 4. So as you can see, every time you put a factor, all you have to do is tack on a plus or minus. Because if the term is positive, then negative times a negative is a positive. If the number is negative, a negative times a positive. So it's going to take on both the plus and minus of that number. So now the possible factors of -3, which is your p, remember, and the possible factors of 4, which is the q on the bottom, is going to be the possibles on top and the possibles on the bottom. Okay? So if you just do all the possible permutations of that, you get plus or minus 1, plus or minus 3, plus or minus 1/2, plus or minus 3/2, plus or minus 3/4. Now, a lot of these you probably can guess which one is, but you know that one. Sometimes they're duplicated, but sometimes they're not. So, but the plus or minus 1/2, okay, is taking the first one of the top divided by the bottom one, the middle one, and the bottom. That's how you get the negative 1/2. You're like, what about the 3/2? Well, it's the last one on top and about the middle one on the bottom. Now there are 1, 2, 3, 4, 5, 6. There are 6 possible ratios. So that means there's 12 possibilities because each one's got a plus or minus in front of it. So there are 12 possible rational zeros here. 12. And you're like, 12? That means that any one of those 12 could be it? Yes, that's true. But look at the alternative. How many rational numbers are there in the world? Yeah, there's infinite number. But this particular polynomial, if it has a rational zero, it's one of those 12. So you basically downsized infinite to 12. So that was the alternative, remember. So like, what do? We have to test each one of those numbers? Yes, we do. Okay, we're not going to do that here. Okay, because all we wanted to do here is just figure out the possibilities. So we were trying to get our feet wet, so to speak, in this. So using the rational zero theorem. So these are the 12 possible rational zeros if it has any. Okay. Now this one, I think we're going to find the zeros of the polynomial function. So we're going to find the zeros of x to the third plus x to the second minus 5x minus 2. Okay, so if you set that equal to 0, you're going to figure out what values of x. Now remember, this is degree 3, right? So there's going to be 3 solutions to this. So here goes. We begin by listing all possible rational zeros. What are the possible p-values? The top. Remember, those are the possible ones of the constant -2. So what are the possible factors of -2? If you said 1 times -2 and -1 times a +2, that's it. So it's plus or minus 1 and plus or minus 2. Okay? Now the bottom one is, the q is just a leading coefficient, which is only a 1. So you only got possibilities of plus or minus 1. So here's his next step is plus or minus 1, plus or minus 2 for the -2, and the plus or minus 1 on the bottom. So if you do all the possible permutations of that, it's going to be plus or minus 1, comma, plus or minus 2. So yeah, this one's only got 4 choices. You're like, do you know how many choices you're going to have going in? Not really. Okay. Not very many people can tell you how many zeros you're going to have, rational zeros you can possibly have just by looking at it like that. So this one had 4 altogether, 1, -1, 2, and -2. If you remember, the previous one had 12. So, but this one right here, if it has a rational zero, it's one of those 4 numbers, 1, -1, 2, or -2. So now we're going to use synthetic division to see if we can find a rational zero among the 4 possible rational zeros. So the possible rational zeros are, like I said, 1, -1, 2, and -2. We will use synthetic division to test the possible rational zeros. So they test -2 first. They use synthetic division. They go through the process. We learned synthetic division already. And we're using the remainder theorem. What's the remainder? Yeah, it's 4. And 4 does not give me 0. Okay, so therefore, by the factor theorem, this is not a 0. So now using the remainder theorem here, put -1 in, and we add 3 at the end, right? So because that's the remainder theorem. And by the factor theorem, that does not give me 0, so therefore the -1 is not 0. It does not give me a 0. So I tested -2 and -1, and neither one are 0. So if this does indeed have a rational 0, it's the positive numbers. It's one of those positive numbers, possibly both. So neither -2 and -1 is a 0. We continue testing possible rational zeros. So we found -2 and -1 are not zeros, so we continue testing the 1 and the 2. So I tested the 1, and I get what? It's going to be -5. And again, -5 is not 0, so by the factor theorem, that 1 is not 0. So I'm down to my last choice, okay? If 2 is a 0, then I'm good. I think I found one. And it is. The remainder is 0. Now, we do this on purpose here. We want you to go through all 4 possibilities. A lot of times, you don't have to test all the possibilities before you find the first 0. So we kind of did this on purpose. We wanted to test the first 3 to show you those are not zeros with that last one. But sometimes that does happen. Sometimes you're just very unlucky and you find the 0 at the very last. Okay? So, and you got to be very careful with your synthetic division. Okay? Because if you make a mistake on your synthetic division, you can mistakenly discard a possible 0. And or you could make a mistake the other way and it does become 0 and it really wasn't. So you got to be very careful on the synthetic division. I'm kind of going through the synthetic division aspect of this rather quickly because we've done that before. Okay, so you got to be very careful with your synthetic division. If you're not comfortable with synthetic division, then what you're going to have to do is plug these numbers in and see if it's 0 or not. So either way it would work. Alrighty. By any stretch of the imagination, this is not a quick fix. These kind of problems don't come out quickly. They take a little bit of time. Okay, the times that you finish math problems in less than a minute are pretty much gone. I mean, because it's going to take a little while to do problems from here on out in the future. So they take a while to do. So, but in this case, 2 is a 0. So we have found a rational 0 at x equals 2. So that means x cubed plus x squared minus 5x minus 2 can be factored out because x minus 2 is a factor. And remember, the remaining part of that quotient is x, the 1, the 3, and the 1. So it's going to be x squared plus 3x plus 1. That's the remaining factor. But you're like, well, wait a minute. You've gone through all 4 possibilities. And that is true. I have gone through all 4 possibilities, and I've still got 2 that I haven't found yet. But remember, on quadratics, you have other ways to solve a quadratic other than the rational root test. It is true that there's no more rational zeros. Only the 2, x equals 2 is a rational 0. It has 2 more. Remember, I have 3 answers altogether, 3 zeros altogether. This one has 2 more, but it's a quadratic. But like I said, we have another way to solve a quadratic equation by the quadratic formula or factoring if it factors. I doubt they factored this time. So if we use the quadratic formula, and that's what they do here, you get at the end negative 3 plus or minus the square root of 5 over 2. But notice the radical 5. That means the number is not rational. It's an irrational number. So as a matter of fact, the other 2 could have been complex if it just turned out, if the discriminant was negative here, it would have been complex numbers. So remember, you got basically 3 types. You got rational zeros, irrational zeros, which make up the real numbers, and then there's the complex numbers. So there, when you're finding your zeros, it's going to fall into 3 categories: rational, irrational, or complex. The rational root test only finds the rationals. But what our hopes are is it will find enough of them, enough of the problems are rational that you can find the remaining ones, which might be irrational or complex. So that's the hope here. You're like, well, what if you don't? What if you have 4 complex and 1 rational? What do you do then? Not much we can do at this point. Okay, there are other ways to do it, but this technique is very limited in what it can do. But all the problems that you're going to encounter here, if you have 4 solutions, okay, 2 of them will probably be rational. So you can knock it down to a quadratic. If you have 5 zeros, if the degree is 5, 3 of them are probably going to be rational and 2 of them are going to be complex or irrational. So basically all of them are going to be rational except for 2. And then even the last 2 could be rational as well. Okay, so in this case, the zeros are going to be 2, negative 3 plus radical 5 over 2, and negative 3 minus radical 5 over 2. And that's the solution set. 1 rational and 2 irrational zeros for this problem. Okay, so it's very important, guys, that you're taking notes on this. Okay, write this problem down. This is a very good example of finding the rational zeros and finding all the solutions altogether. So I know I've been beating on this from day one, but I'm hopefully somebody will listen to me. Okay, writing this down, pause the slides and then write the slide down, okay, in your notes, and it helps. Okay, but you got to do that. You can't just watch me do it and just try to remember everything you learn through visual. Okay, because you're going to forget. Time's going to go by. You're going to forget all this stuff. If you write it down, you've got something to refer back to. Okay, that's my preaching for today on that. So, all right, so let's move on. Properties of roots and polynomial equations. Okay, so if a polynomial equation is degree n, then counting the multiple roots separately, the equation has n roots. Okay, like I just said a while ago, if the degree is 3, you're going to have 3 answers. If the degree is 5, you're going to have 5 solutions. Okay, now sometimes the roots duplicate. And you remember we talked about multiplicity, so sometimes they duplicate. So in other words, 1 might be a solution, not but one time, but twice. So when you're using the rational root test, even then, if you find 2 as a solution, it might be a solution again. So you have to actually go through there and test 2 again on the remaining quotient after you divide and find out the remainder was 0. So once you find out the degree is 0, then you use that as your new polynomial that you're testing, because you're just breaking it down one step at a time. Okay, if a plus bi is a root of a polynomial equation with real coefficients b not equal to 0, then the imaginary number a minus bi is also a root. Imaginary roots, if they exist, occur in conjugate pairs, and that's the important part. So in other words, if 2 plus 3i is a solution, then you're guaranteed to have 2 minus 3i as the solutions, as long as your coefficients are real numbers. If your coefficients are real numbers, that's going to happen every time. So they come in conjugate pairs. So if they tell you that 5 plus 3i is a solution, then 5 minus 3i is guaranteed to be a solution. They don't even have to give that to you. Okay? You know that from this property. Actually, we have that. We call this the conjugate pair theorem, and they don't name it in this book that thing, but it's called a conjugate pair theorem. And this book kind of downplays the importance of this, but it is quite important when you're actually trying to solve these equations, because it's you're trying to find the zeros and you're trying to find them as efficient as you can. And so if you have 4 solutions, you got 4. And they tell you 2 plus 3i, wouldn't it be great to know that there's another solution, 2 minus 3i? Because now you got from down to 3 down to 2. All you got to do is find the remaining 2 at that point. So it's pretty cool. So, all right. So let's solve this polynomial equation. We got 3. It's 3. Notice there's 3 slides because it's quite lengthy. It's x to the 4th minus 6x to the 3rd plus 22x squared minus 30x plus 13 equals 0. Now think about how this problem, guys, before this class started. I mean, just think about it. I mean, take this equation, go back to intermediate algebra, and your teacher gave you this equation to solve. If you're like me, you would just kind of like stare at them like, I have no idea. I can't factor that thing. So x to the 4th minus 6x, there'd be no way I could do that. Okay? So learning this little bit is giving you guys the ability to solve these types of equations, and it's not all about factoring. Okay? You can find solutions to equations without factoring so much. I mean, factoring is still a part of this, but it takes much more than factoring in order to solve this. So let's use the rational zero theorem. Okay, so we begin by possible factors. So we got plus or minus 1 and plus or minus 13, because that's the possibilities for the p, the constant term, 13 at the end, and the plus or minus 1 at the beginning. So we have those possibilities. So we got, basically, if you look at through all the permutations of that, it's going to be 1, negative 1, 13, and negative 13. Those are the 4 possibilities again. Okay, and now remember, guys, how many solutions does this thing have? Yeah, it has 4. Okay, it has 4 zeros. So if it has 4 zeros, we're hoping that we can find 2 rational zeros out of this. You're like, why? Well, it's because if the degree is 4 and you find 1, you're down to 3. Okay? And when you're down to 3, okay, then they come in conjugate pairs. So there's got to be another rational zero, because irrational zeros, I don't think that you're going to get an irrational zero off of this either. So you're probably going to get 2 rationals and 2 either irrationals or 2 complex, probably. Okay, let's see. So we test negative 1 through the remainder theorem, and you get negative 72. And by the factor theorem, that's not going to work. Then we're going to try the 1, And, oh, 1's works. Okay, 1 is a 0. Okay, now you can't give up on 1. And you're like, why not? Because if you give up on 1, it might be a 0 again. So you see the remainder, 1, -5, -17, -13, 0. So the new polynomial is going to be x cubed, because you remember you got to go down by 1, minus 5x squared minus 17x minus 13. Okay, so that's our new polynomial, but I'm going to have to test 1 again in that because it might be a 0 again. So x equals 1 is a root of the polynomial, and we can rewrite the equation in factored form. Okay, so x to the 4th minus 6x cubed plus 22x squared minus 30x plus 13. So x minus 1 was a factor. So x cubed minus 5x squared plus 17x minus 13 was the remainder. So that's my new polynomial. So in factored form, that's what we're going to have. So now we're going to solve x to the 3rd minus 5x squared plus 17x minus 13 equals 0. Now remember, you still got those 4 possibilities, okay? But we've already tested -1, and it didn't work on the original. So we begin by testing all those again, and since -1 didn't work the first time, it's not going to work this time either. So because -1 did not work on the original polynomial, it is not necessary to test that value again. But 1 might work again, so we test 1 again. Oh, and look at there, it is 0 again. So we put 1 back into the next quotient, 1, -5, 17, and -13, and the remainder was 0 once again. So we got multiplicity 2 now. So x equals 1 twice, and then we got 2 more coming, and that's going to come off that. So x equals 1 is a repeated root for the polynomial. So the original polynomial can now be written as x minus 1 times x minus 1, or you can write it as x minus 1 squared, times x squared minus 4x plus 13. That's quadratic, right? So if it's quadratic, we have 2 answers there too. You're like, well, do you need to test a 13 and then -13? You could, but it won't work. But once you get it down to a quadratic, you don't want to go down, you don't want to use the rational root test all the way down that many times. So once you get it down to a quadratic, go ahead and use the quadratic formula. So if you had 4 answers like this one does, you found 2, that knocks it down to a quadratic, in this case x squared minus 4x plus 13. Okay, then just use the quadratic formula on the remaining part. And the remaining part would be 4 plus or minus the square root of -36 over 2. Note that -36 is discriminant. And so we work that out, and it's going to be 2 plus or minus 3i. Notice the conjugate pairs there, guys. 2 plus 3i and 2 minus 3i. Notice the conjugate pairs. Okay? So remember, what are our solutions now before I click at this thing again? We got 1 again, that's twice, that's 1 twice, so it's multiplicity 2, and then 2 plus 3i and 2 minus 3i. That's 4 zeros. I found all 4 of them. So the solution set is 1, 1, 2 plus 3i, and 2 minus 3i. Okay? Now, for those who are thinkers beyond what we actually do in this class, some people might think, well, what if it does not have any rational zeros? And the degree is 4 and you have no rational zeros. Then this technique won't help you. As a matter of fact, finding those zeros would be very daunting. Okay, so this thing, even though it's pretty sweet, it is limited in what it can do. Okay, so the ones you're going to be able to find, okay, if it has degree 5, you're probably guaranteed to have 3 of them that are rational. Okay, so they're not going to make you find, 4 complex solutions. Okay, and there's only 1 rational zero. So if their degree is 6, there's probably going to be 4 rational zeros, and then some of those 4 might be repeated. In this case, there was a 1 that was repeated. Okay, so as beautiful as this technique is, it does have its limitations. Okay, all right, let's go to the next slide. The fundamental theorem of algebra. So if f of x is a polynomial of degree n, then if the n greater than or equal to 1, then the equation f of x equals 0 has at least 1 complex root. Okay, now notice that the degree is n greater than 1, the equation f of x equals 0 has at least 1 complex root. Now that's if the degree, that's the fundamental theorem of algebra. What that basically is saying is if you don't have real coefficients, if there is a coefficient that is imaginary or complex, then you're guaranteed to have one complex, 0. That's basically what it's saying. And the linear factorization theorem, a sub n, so you have that, remember that generic form of a polynomial, degree n. Then f of x equals a sub n times x minus c1, x minus c2, all the way out to x minus cn, where cn, c1, c2, all the way out to cn are complex numbers, possibly real and not necessarily distinct. In other words, remember we can have repeated zeros. So C2 could be the same thing as C3, okay? So C1, C2, C3, all of those are the zeros of the polynomial. And some of those zeros could be real, and some of them could be complex. So what this is basically helping you with is this idea, okay? If you tell me that 2 and 5 are zeros of a polynomial, if 2 and 5 are zeros, then x minus 2 times x minus 5 are factors. That's what this is basically saying. Because if the zeros are there, then x minus that number is how it has to be a factor. We've actually applied this already. This just gives it a formal meaning here. So if 3 is a 0, then x minus 3 is a 0. If negative 4 is a 0, then x plus 4, because x minus a negative 4 is x plus 4, is a factor. So that's what the linear factorization theorem is saying. See, what you've been used to is this. If you give me x minus 3 times x minus 2 equals 0, then x equals 3 and x equals 2 are the zeros, right? Just set each factor equal to 0, okay, and solve. What this is basically saying is it allows you to go up the other direction, okay? If they're saying 2 and 3 are zeros, then x minus 3 was a factor and x minus 2 was a factor as well. Okay, so it works both ways. Okay, that's all the linear factorization theorem is saying. Okay, so in other words, you guys have been accustomed to working one direction on that. Okay, once you get it in factored form, set each factor equal to 0, and those are your zeros. Here, these are the zeros. Well, this is the factored form that gave you that. That's what this is saying in a nutshell. Okay, all right, let's move on. Example. Finding a polynomial function with the given zeros. So here we get to use that complete factorization theorem. So find a third degree polynomial, the degree is 3, function with real coefficients that has negative 3 as a 0 and I as zeros, and such that f of 1 equals, I believe that's a 6. Nope, it's an 8. It's an 8. So f of 1 equals 8. So solution. Because I is a 0 and the polynomial has real coefficients, because they tell me that, the conjugate, negative I, is also a 0. And so we can use that with the linear factorization theorem. So f of x equals a sub n. Remember that leading coefficient out there. And then x minus c1, x minus c2 times x minus out to cn. But in this case, it's just going to stop at c3. So it's x minus c1, x minus c2, x minus c3. You're like, why does it stop at c3? Because we only got 3 zeros, remember? Okay. 3 zeros are 1. Sorry, it's not 1. It's negative 3, I, and negative I. So it's going to be x plus 3, x minus I, and x plus I. Now, they don't tell you this here, and it's very easy to make this mistake. Is the next step I get a sub n equals x cubed plus 3x squared plus x plus 3. Now what they don't tell you is it's very tempting to try to multiply x plus 3 times x minus I, because those are the first two factors. If you do that, you create more problems for yourself. Okay, what I would suggest is to multiply the x minus I and the x plus I at the end. Foil that out first. You're like, why? Because they're difference of squares. And then the i's cancel there. And you want the i's to go away as quickly as possible, because, and they will cancel immediately even if you multiply the first two together. But it's easier to get rid of them if you multiply the x minus I, x plus I. Because if you multiply the last two together, you get x squared plus 1. Okay? When you multiply x minus I times x plus I, you get x squared plus 1. Take that x squared plus 1 and multiply by the x plus 3 instead. They don't tell you that here. They just hope that you kind of pick these things up at the end. I'm just giving you that hint now. Okay, so this is why you write these things down on your slide. You pause them, you write down what I have up there on the board, and you make these notes like this. Multiply these two together first. And if you do that, so you multiply x minus I, x plus I, you'll get the x squared plus 1. And then multiply that by the x plus 3. That turns out to be x cubed plus 3x squared plus x plus 3. Remember that a sub n out there? That's some coefficient. That's determined by what they tell me f of 1 equals 8 is. So you're like, well, we haven't used that. Well, here we do. So f of 1 is equals to a sub n. You plug the 1 in for the x, and that should equal 8. So you do the math. 1 cubed plus 3 times 1 squared plus 1 plus 3. All that's going to equal to what? 8. So you have 8 a sub n equals 8. So a sub n happens to be 1 in this case. I wish they had made this a 16, made that instead of making saying f of 1 equals 8, I wish they would have made f of 1 equals 16. And the reason that is because at least to show you that sometimes that leading number is not always 1. Okay, this doesn't really teach us anything because if it's 1, then you might as well not even have anything at all. I wish they had made that a 16 outside to show you that a sub n could be a 2. You know, what if it was 2? Well, then you'd have to take that 2 and distribute through the parentheses. Okay, that's what you would have had to do. Okay, but they didn't. They made it a 1, so it's really, you can just kind of throw it out because 1 times anything is that. So the polynomial function is f of x equals x to the third plus 3x squared plus x plus 3. And so you would have got that if you would have just ignored f of 1 equals 8 in this case. And that's why I wish they had not done that. Because if they had done that, if you were doing this on a test, that would have been the same answer if you mistakenly just ignored f of 1 equals 8. Okay? And I won't do that. So on exam, you're going to see a lot of times that a sub n is going to be a number that's not 1. Okay? So like I said, I wish they would have made f of 1 equals 16. And that would have showed you that a sub n would have to be 2 in that particular case. Okay, so just be aware of that. All right. Now the Descartes rule of signs. All right. Now the Descartes rule of signs doesn't have really anything to do with the rational root test. But it has to do with finding the possibilities of real numbers and complex numbers. So f of x is, again, that generic form of the polynomial. Okay. Every time people see that, it scares them a little bit. But I just call it, oh, it's a generic polynomial. Okay? So if you can think of it just kind of a, in that fashion, it's not as scary anymore. Just give it, oh, it's just a generic polynomial function. So a sub n, a sub n, blah, 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 all the way out to a sub 0. Okay? Be a polynomial function with real coefficients. So all the a's are going to be non-complex. They're going to be just real numbers. Okay, this is what the Descartes rule of signs tells me. The number of positive real zeros of f is either the same as the number of sign changes of f of x or less than that number of sign changes of f of x by a positive even integer. If f of x has only one variation in sign, then f of x has exactly one positive real number. Okay? So this is what it basically say. Go through f of x and see how many sign changes do you have. Okay, you don't want to put any missing terms in there. So just go through one term to the next, ignore any missing terms, and let's say there was 3 sign changes. And what does that mean, sign changes? Well, a sign change is when the first term is plus and the next term is a minus. That's a sign change. Okay, so from plus to minus is a sign change. Okay, let's say the third term is also a minus. That's not a sign change. And the next term is a plus. Oh, that's a sign change. We got 2 sign changes. So when you go from one term to the next term, if there's a sign change, that you count it. If 2 consecutive terms are both pluses, or 2 consecutive terms are minus, then that's not a sign change. But if consecutive terms have a different sign, then you count it. Now let's say there were 3 sign changes. Then what this is basically saying is you're going to have 3 real solutions to this problem, or less than that, by an even number. What that basically means is there's either going to be 3 or 1. So you're guaranteed 1. And let's get really outrageous. Let's say there's 7 sign changes. So if there's 7 sign changes, then that means there's going to be 7 reals or 5 reals. Notice I'm saying or 3 reals or 1 real. What if there's 4 sign changes? Well, then there's 4 real solutions or 2 real solutions or 0 real solutions. Now, understand what I'm saying here, guys. Okay? I'm not saying these are the solutions again. I'm not saying that at all. I'm saying these are the possibilities of this. Okay? So, if there were 3 sign changes, I know I'm going to either get 3 or 1 real solutions, positive real solutions. But, you know, what are they? I have no idea. That doesn't tell me anything. So the Descartes rule of signs is not a way to find the solutions. It gives you the possibilities of the solutions. Okay? And you're like, how can this be helpful? Well, think about it. Let's say there was just 1 sign change. And that means you're going to have 1 positive real solution. Positive real solution. You're guaranteed that. Okay? You're guaranteed to have 1 positive real number. Okay? If you're guaranteed to have 1 positive real number, then that pretty much tells me it's got to be a rational number. Okay? So if that's a rational number, then I know I can use the rational root test to find that 1 rational 0. Now you're like, well, yeah, but what if there was 7? Well, it doesn't help much, because if you have 7 sign changes, then that means you could have 7, 5, 3, or 1. But it does help in this regard. Let's say you had 7. I mean, let's get really outrageous. Let's say you had 7 positive real solutions, up to 7. Well, let's say you're up to 2 already. You've already found 2. Then what do you know? Well, you know you're going to have at least 1 more, right? Because you got to have an odd number leading up to 7. 7, 5, 3, or 1. So if you have 2, then you're guaranteed to have at least 1 more. Okay? So that's why it's kind of helpful, because it kind of directs you to how many you should have. So you know if you had up to 7, you found 2, then you know you got 1 more coming somewhere, and you just have to find it. So it kind of directs you to the right place. Now, the number of negative real zeros. Remember, this first one just tells us about the positive real zeros. This one's about the negative real zeros. Okay? So the number of negative real zeros of f is either the same as the number of sign changes in f of negative x, okay, or less than that by an even number. Okay? So let's say there were 4 sign changes. Okay? Then that means I'm going to get 4, 2, or 0 negative real zeros. And let's say I found 1 already. Remember, it's going to be 4, 2, or 0. I found 1 already. Well, then I know I'm guaranteed to find another one, 2. Okay? So that could be all of them. But if I found another one after that and I have 3, then I know I'm going to have 4 then, right? So because they kind of come in even numbers if there's 4 sign changes on that. You're like, well, these are the same thing. No, it's not. Okay? The first one is to find the number of sign changes in just the original function. And that'll give you the possible positive real zeros. The second one, you have to plug negative x in first, do the calculation, and look at the new sign changes for the f of negative x. Then those number of sign changes gives you something to look at for the negative real zeros. Okay? Note, this has nothing to do with complex, other than it's the residual, what I call the residual ones. So let's say the degree is, let's say the degree is 5. Okay? And you found there could be 2 positive reals, 2 negative reals, okay? And, well, then that's, it wouldn't be that, because if it's 2 and then 1, let's say there's 1 negative real. So if you had 2 positive reals, okay, that's 2, and then 1 negative real, that's 3, okay? Then how many is left? The degree is 5. Well, 2. Well, then the residual, the 2 would have to be complex, because you could have positive reals, negative reals, or complex. So if you found that you could have two positive reals, one negative real, then that means the residual has to be complex. Okay, so let's look at an example of this. Now understand, guys, that the DesCartes rule of signs do not find the zeros for me. They will not find them for you. Okay, this just gives you the possibilities. Okay, let's look at an example. Using the DesCartes rule of signs, determine the possible positive and negative real zeros of f of x equals that big long expression. Okay, now note that to find the possible positive reals, we count the number of sign changes. Now remember, any missing terms, if it has any, just disregard. So from the first term to the second term, remember, from positive to negative, yep, that's a sign change. So just keep count. That's one. From the second term to the third term, it went from negative to positive. Oh, that's another sign change. That's two. From the third term to the fourth term, it went from a 71x squared to a negative 154x. So that's 3. And then from a negative 154x to a positive 120, that's 4. There are 4 sign changes there. Okay? So there are 4 variations of sign. So how many positive reals might I have? If you said 4, 2, or 0, you'd be correct. Now you're like, but that doesn't tell me what they are. No, it doesn't. That's not what the purpose of the DesCartes rule of signs are. It just gives you the possibilities. So it's 4, 2, or none positive real solutions. Okay? The number of positive real zeros are 4, 2, or 0, which is what I just said. Okay? Now, on the number 2, find the possibilities for the negative real zeros and count the variation signs of that one. So we first have to calculate f of negative x. So a negative x to the fourth, which is x to the fourth, and then negative 14 times negative x cubed is a positive 14x cubed. And then 7 times negative x squared is a positive, 71x squared. And then negative 154 minus x times a negative x is a positive 154x. And then plus 120. Count the variations there. Do you see any? Positive x to the fourth plus, that's not a variation. 14x cubed plus 71x squared, no. 71x squared plus 154x, nope. 154x plus 120, nope. There are no variations of signs in that one. So what does that tell me? There are 0 negative real zeros. That means there are no negative rational zeros, and there are no negative irrational zeros. Okay? They don't have any negative zeros at all. They could be complex, but there's no negative real zeros. So remember the rational root test? And when we were doing that one a while ago and had all those fractions and we were testing those possibilities, none of those negatives would have worked in a problem like this. Okay, so I wouldn't even have to test all the negative ones. Do you see how that this could be beneficial? So, because if it's negative real, that would include the negative rationals. Okay, so there are no variations of sign, so there are no negative real zeros of f. Okay, so this is kind of where these PowerPoints end, but I want to talk about one thing about this problem. How many zeros does this thing have? I believe the degree is 4, correct? Okay, so you have 4 answers. Okay, so you have 4 zeros to this thing. They could be rational, they could be irrational, or they could be complex, right? Okay, now some of those could be positive, right? Yes, but none of those can be negative because of the second one. So let's talk about positive, negative, and complex. Remember, there are 4 answers, right? So if all 4 were positive real zeros, if that was the case, how many negative real zeros would there be? None, because we know there's none by the second one. How about complex? Well, if they're all 4 real and you have no negative reals, the remaining would have to be complex, but there is no remaining because I only have 4 to begin with. So you could have 4 positive reals, no negative reals, and no complex. Now what's the next choice? Well, it could be 2 negative reals. Remember, 4, 2, or 0. So what if there are 2 positive reals? Well, if there's 2 positive reals, how many negative reals are they? Oh, it's still 0. So we got 2 positive reals, 0 negative reals. Then the residual would be complex, which means there's 2 more. So it'd be 2, 0, or 2. 2 positive reals, 0 negative reals, and 2 complex. But there was a third possibility of 0 positive reals. And so 0 positive reals, again, there's no negative reals by the second one. Then that means all 4 of them would have to be complex. So you think about it, it could be 4, 0, 0, 2, 0, 2, or 0, 0, 4. Okay, in that regard. So those are your 3 possibilities. You have 3 possible solution types, if you will. Okay, solution types. Let's call them solution types. Okay, you could have 4 positive reals, no negative reals, and no complex. That's one solution type. You can have 2 positive reals, no negative reals, and 2 complex, and that's another type. Or you could have no positive reals, no negative reals, and 4 complex. That's the third solution type. Okay, so there's 3 possibilities. And you're like, yeah, but that doesn't help me find the solutions of that problem. Yes, it does. It does. So if you were trying to use the rational root test, let's say on this thing, if you were to find them, you won't need to test any of the negative ones. If they're going to work, they have to be some of the positive ones. You might get lucky in finding at least 1 positive real. But if you find 1 positive real, then you know you have another one, right? So if you find 1 positive rational number that works, because you're like, well, how do you know I have another one? Well, it's either 4, 2, or none, right? So if you find 1 positive one, then you know you're guaranteed to have another one because it's either 4, 2, or none. So another positive number would have to work. So that's kind of how this kind of works. Yeah, it doesn't give you the solutions directly, but it directs you in the right path of getting there. Okay, so alrighty. So that concludes this video. I know it's quite lengthy, but it is worth it. And I'm hoping you guys will not only listen to what I'm saying here, I also want you to write these things down. We're getting to a point now that if you're not writing stuff down, you might as well not to watch the videos at all, really, because it's so deep sometimes that you've got to get the nuances of it, and that means you got to write them down. Okay, so I really, really, really would like you guys to write these things down. I know you're sick and tired of me saying that, but it's not going to stop because I want you to be successful in the class, and this is part of the success. Okay, not too many people are successful in this class who don't do these things, unless you didn't need my help to begin with. So some people are in that situation. They have so much math background that this is old news to them. Maybe they don't need to write it down, but a typical person who's in this class who meets the prerequisites and a general student, just a general student, needs to do this to be successful in the class. Okay, so but I can't make you do it, but I would really like for you to do that. But anyway, you guys have a good day, and if you have any questions, as always, you let me know, and I'll see you on the next video.